Good afternoon, everyone. Thank you very much for being here. My name is Marcos Vasconcelos, and I'm a PhD candidate here at the Department of Electrical Engineering at the University of Maryland, College Park. And today I'm going to talk about a new class of problems that I have been studying in my PhD of remote estimation over a channel model called the collision channel. And the title of my talk is Optimal Threshold Strategies for Estimation over the Collision Channel with Communication Costs. The outline of my talk is the following. First, I will talk about the context and motivation for studying such problems. Then I will state formally the problem statement. But essentially, the class of problems that we're interested in studying is the following. When you have a sensor making measurements at one location and an estimator in a different location forming estimates of this measurement using information sent by the sensor over a channel, a communication channel or network. And so I will discuss the formulation of this problem, and then I'll state the main results and provide sketch of the proofs. The main results being the existence of optimal thresholds. Then I will talk about the symmetry properties of optimal thresholds. We'll talk more about that later. And then I will derive an iterative method for the solution of the optimization problem and show its convergence. And I will finish with a conclusion and future work. So we started looking at these problems in the following context. You have a network of decision makers cooperating to solve a problem. Okay? So in this figure here, you have multiple decision makers interacting with a network. So the anatomy, if you look closer here at in this figure on the right, each decision maker makes a local observation or measurement about maybe a physical quantity it's observing. And then there is this interaction with the network in the form of transmitted and received packets. So the applications of such systems are, very wide. For example, you can model distributed sensor networks, also detection, computation, and control. So this is the main framework that we're interested in. Now, when I started looking at these problems, I wanted to do something. We needed to do something new, right? So we looked at existing models for the network. And previous work had already considered, for example, consensus problems in which the agents are trying to compute a function in a distributed manner. And the network was modeled by an incomplete graph. There were also problems, for example, in distributed control and distributed sensing, in which the network was modeled as a network of erasure channels. And then I thought, what can be different here? What is a new feature that no one had explored so far? And I noticed that no one had worked on interference in the network. So that's what I wanted to explore in my PhD, to study the effect of interference in network estimation in this context here. So the first problem that I formulated was the following. You have multiple sensors, each one making a measurement. These measurements are independent, and they communicate with a remote estimator through a collision channel. This collision channel is a very simple model for interference that works as follows. If more than one transmission occurs, if more than one sensor transmits, then the output of the channel will be a collision. If no sensors transmit, then what you have here at the channel output is an erasure. Transmission is only successful when a single sensor transmits. Okay, so that's how I'm capturing the effect of interference. If two or more people talk at the same time, then the communication doesn't go through. And the objective here in this problem was to optimize the sensors and the estimator such that you minimize a mean square cost. Okay? So that was the first problem that I formulated. And for this problem, we obtained the following result. The optimal policies that minimize the mean square cost have this threshold structure, okay, where I don't transmit if my observation falls within an interval defined by thresholds A and B. And if my observations fall outside that interval, I transmit. So the policies have this form here, okay? 0 meaning I don't transmit, and 1 meaning transmission. Okay, so I proved that the optimal communication policies have a deterministic threshold structure. By deterministic, I mean that randomized policies don't get you anything extra. So you can restrict yourself to deterministic threshold policies. And also that this structure holds for any set of independent continuous random variables. So it could be any number of independent observations here. And they could come, the observations could come from any distribution, okay? As long as it's continuous. Now, there is an even simpler model, which is going to be the focus of this talk, in which I only have one sensor transmitting and one estimator, and the sensor will make an observation of this random variable x, decide whether to transmit or not over a collision channel, and the estimator will observe the output of the channel, okay? So now the channel works as follows. If you decide to transmit, the channel will pay, the decision maker or the sensor will pay a cost. This cost can come from, for example, the battery, right? So it's a price on the transmission that you're paying. Every time you transmit, you pay a cost. So the input of the channel will be a measurement, will be the measurement itself, x. With some probability, the measurement the packet will go through the channel, and with the complement of that probability, the estimator will observe a collision. You can think of this as the channel being occupied or not at the same time that you're transmitting. Or you can decide not to transmit, and therefore you don't pay any cost, so the channel is free. And what the estimator will observe here is just the absence of channel input. And the cost that you're trying to minimize is a combination of the variance of the estimation error and the communication cost. So this is the problem. This is an even simpler problem than the one I just described. That will be the focus of this talk. Okay? So for this problem, the class of communication policies can be restricted without loss of optimality to being threshold policies as well. And the estimator will just will operate as follows. So if the channel output is the packet the packet that contains the measurement, then I just output that packet, the content of that packet. If the estimator observes an erasure, then you have some value here, some real number that will represent that event. So I'll call this a representation symbol for the erasure. And the same will happen for in the case if you have a collision. And you have a representation symbol for the collision as well. And using these two these two structures for the sensor and the estimator, the optimization problem becomes minimizing the threshold A, B, and representation points X hat erasure and X hat collision. That minimizes this cost here. Okay. So when we look at this cost here, I thought that this was, and it is true, this is just like a binary quantization problem. Okay. So if you have worked on quantization before, this is the kind of cost that you have. But you only have two quantization regions, the interval AB and the complement. Okay? And the interesting feature about this quantization problem is that the distortion functions across representation, across quantization regions are distinct. And this is a new feature of this problem. This is what turns this problem interesting. Okay? Why is this problem relevant? Well, it's a very simple problem, canonical problem, okay? But this problem is important because it introduces a new channel model for network control and estimation. No one had worked or defined this kind of problem, defined this kind of channel precisely in the literature. So this is the first contribution. Second contribution is that we showed that the presence of collisions in the channel cause asymmetry of optimal thresholds. And this is a new feature as well. Most of the work in remote estimation obtain structures that are symmetric. Okay? And this is a distinct feature. And the other distinct the other contribution is because the problem is so simple and so canonical, this can be used as a building block for more complicated problems. In particular, the sequential estimation problems, because this is a one-shot estimation problem. And also, if you're familiar with the packet drop channel, this is a generalization of a packet drop channel, because if the collision symbol is equal to the erasure symbol, this becomes just packet drop channel, okay? And also, the collision channel is a more appropriate model for wireless communications networks. Now, I'll get to the more technical part of the talk now. So we're interested in minimizing this cost here over the thresholds and the representation points, subject to the constraint that one threshold must be less than or equal to the other. Okay? For such problem, one necessary optimality condition is that the no transmission interval must satisfy this inequality here. And this will give us expressions for the optimal thresholds in terms of the pair of representation points x hat. Okay, so the representation points can be expressed by these functions here. Sorry, the thresholds can be represented by these functions. And then, without loss of optimality, I may define a new cost, JQ, which uses these thresholds here in this function. And then this becomes an unconstrained optimization problem, nonlinear optimization problem, in which I want to minimize JQ over x hat in R2. And this is the main mathematical object of this talk. So, the first result is an existence result that shows that if the cost the communication cost is positive but finite, the global minimizer of JQ exists. Well, this is the reason why we worried about this is because if you're using any numerical method to optimize a cost function, and this is a non-convex cost function, if we don't guarantee that the minimizer exists, then the numerical method may not converge, right? So this guarantees that the optimal thresholds are finite, and I may search them using a numerical method. May search for them using a numerical method. And here's the sketch of this is the cost. This is how the cost looks like. And the sketch of the proof is as follows. First, we show that the cost function is continuous on R2, and then we must show that there exists a point x hat star such that the value of that point x hat star is less than or equal to the value of the cost as the norm of the argument goes to infinity. And this is a property similar to coercivity, where the cost goes to infinity as the norm goes to infinity. If something like this happens and the cost is continuous, then you guarantee that the minimizer exists. Now, two examples, if you look here, I don't know if you can see it from here. For example, if you consider a quadratic function, right, this is a coercive function. This is just to give you an idea, and then the minimizer is here, right? An example of non-coercive function is, for example, the exponential of minus x. So as x goes to infinity, the function goes to 0, right? So the minimizer of this function is at infinity. So we say that the minimizer of this function doesn't exist in R. Okay? So this is a non-coercive function. This is a coercive function. But our cost function here is not coercive. So we needed to come up with this condition here. Now, the proof of the existence of that point is done in two steps. First, we need to show that there exists a symmetric policy that is better than the always transmit and never transmit degenerate policies. So this means that there exists a non-trivial solution to the problem. So this is done here. And the second step is to compute limits, okay? So we must show that the cost as the norm of the argument goes to plus infinity, either goes to plus infinity, which is fine, or it goes to these two values here, which correspond to the cost of always transmit and the never transmit policies. But I just showed that there exists a threshold policy that is better than those. Therefore, the global minimum must exist. Now, the second result pertains to the asymmetry of optimal thresholds. Now, to study the asymmetry, we start by looking at the first order optimality condition, which is the gradient of the function, the cost at the local minima must be equal to 0. Now, when we evaluate the gradient, this will give us this condition, this pair of conditions here, called the centroid conditions. And we can show that x hat, the pair of points, the pair of 0 representation points, always satisfies this condition and corresponds to the best symmetric threshold policy. Okay? Again, symmetric meaning that the thresholds are opposite in sign, right? And asymmetric if one threshold is different than minus the other. So now the question that we're interested in answering is, when are the optimal thresholds asymmetric? Because we know from previous work that when there are collisions, then the optimal were always symmetric. So we wanted something different. And here's the second result. If this function g of beta and rho, beta being the probability of collision and rho the communication cost, is strictly greater than 1/2, the optimal thresholds are asymmetric. So we have a sufficient condition for the asymmetry of optimal thresholds. This function g of beta and rho is related to the determinant of the Hessian at 0, 0. And is given by this expression here. The sketch of the proof is as follows. If the origin, or the point x equal to 0, is a local minimum of the cost, then the Hessian at that point must be positive semi-definite. Now, positive semi-definiteness is equivalent to this function g of beta and rho being less than or equal to 1/2. Now, if g of beta and rho is greater than 1/2, the point 0, 0 cannot be a local minimum. Therefore, symmetric policies cannot be optimal in that case. So here's the plot of instances of these functions, g of beta and rho as a function of beta for rho fixed. And this is what we obtain. So we can see that there is a large range of parameters for beta for which the optimal thresholds are asymmetric. Okay? Now, how do we solve this problem? So we showed so far that the minimizer exists, that there is a condition such that that guarantees the optimality of asymmetric thresholds. How can we compute them? Well, this is a problem that we want to solve. And we are looking for points that satisfy this condition here, right? So these are the critical points of the function. Now this condition can be compactly written as the following fixed point equation. So the representation points are fixed points of this nonlinear map F, which we call the Lloyd's map. And this is given by this expression here. Now, the simplest way to find fixed points, or the most naive way to find fixed points of a nonlinear map, is to iteratively apply the map to some initial condition and observe its convergence. Okay, so that's the most naive way to find fixed points. So now we start from a non-zero initial condition because we already know that 0, 0 is a fixed point. It's always a fixed point. So if we start there, we stay there. Okay, so that's not interesting. We need to start elsewhere. And we iteratively apply the nonlinear map F to this sequence here of representation points. Now, each of these, each iteration of this procedure here consists of two steps. From a pair of representation points x hat k, you update the thresholds according to the equations I showed in the beginning of the talk for A and B. And from these pair of thresholds, you compute the centroids of the new quantization regions. So this pair will define a quantization region, right? So you compute the centroids. Now this is, these are the same steps in the Lloyd-Max algorithm for optimal quantization, for obtaining optimal quantizers. But there is a distinction here. Usually in a binary quantization problem, if you have the same distortion metric across quantization regions, then there is only one threshold. Here, because the functions are asymmetric, you have two. So this is not really the Lloyd-Max algorithm, is a little different. So we call that a modified Lloyd-Max algorithm. Now the question is, does this procedure converge? And the answer is yes. It's possible to show that this modified Lloyd-Max algorithm is globally convergent to a critical point of JQ. And the proof is based on a result by Du and collaborators that appeared on the SIAM Journal of Numerical Analysis. And it consists in finding a compact set C that contains all the critical points of JQ, and to show that this set C is invariant to the map F. And it's possible to find such set. This set is shown here in this figure. It took me a long time to find it, but I did. And this constant L here is a very large but finite number, okay? So the union of these two shaded regions here is the set we're looking for. And we can, globally convergence means that no matter where I start in this region, I will always converge to a critical point of the cost. Now here's two illustrations of the algorithm in operation. So here we consider the standard Gaussian probability of collision equal to 0.3 and communication cost equal to 1. So I don't know if you can see it from there, but here's my initial condition, and this is converging to the minimum of the cost right here. And this is this point here, and it gives you an asymmetric threshold policy. If we reduce the probability of collision from 0.3 to 0.1, something interesting happens though. We start from this initial condition here, and then we converge to a symmetric threshold policy. Now, if you look at the level curves here in this plot, you can see that this is the only minimum. There are no other minimum. So for this combination of parameters here, from this figure, we conclude that the optimal can only be symmetric. Now, just to reinforce the three results of this talk. First, I showed the existence of optimal thresholds. And then I obtained a sufficient condition for the asymmetry of optimal thresholds, which is an important departure from the existing literature in remote estimation. And I re-derived and I proved the global convergence of the modified Lloyd-Max algorithm to solve our problem. And for future work, we are currently working on the sequential version of this problem, which is shown here in this figure at the bottom, where you observe the state of a dynamical system and you decide whether to transmit or not over a collision channel, and the estimator is interested in forming estimates of that state, evolving in time, in real time. Okay? We are also interested in proving the convergence to a global minimum, because so far we have proved the convergence to a local minimum. And we are very interested in using this channel to perform network control and not only estimation. So this brings me to the end of my talk. I will take any questions that you have at this point.
Any questions for the talk? I have a question.
Yes.
Can you give a real-world example of how this can be applied, like a cell phone network or some other?
Yeah, any wireless network. If you take, I don't know what your background is, but if you take if you take a course in communication networks, the collision channel is the standard for modeling a communication network.
So you send some signal, you want to do the estimation of that signal. How precise can you get? If there is some error or not?
Yeah, so right now this is this one-shot problem can be applied, for example, if you're monitoring power grid, for example, okay, wirelessly. Now, the motivation for being a one-shot problem is because if you're trying to detect a catastrophic event like a power outage or something like that, and you want to act quickly, you don't have time to do any sequential analysis of the data, right? So you have a single snapshot of what's going on. But the network at that point may be congested. So we want to deal with that. Does that make sense? Or some other structure, for example, an oil pipeline or something like that, that may burst. There may be some explosion or something, and then you want to act quickly. So that's another example of an application. And the motivation for using a collision channel to model the network is simply because it's the most popular channel for modeling and designing wireless networks, at least that I know. Packet networks. I'm not talking about the physical layer, right? So this is important. This is the network layer or application layer, I think. But this is a different level. This doesn't account for Gaussian noise or anything like that. It's basically congestion. Okay, the network may be congested or not. Does that make sense? Yeah.
So there is no coordination between the senders, right?
No, not at all. Not in this problem. I mean.
So each node can transmit freely.
Yeah. So
policy.
For the purpose of this talk, I'm only studying this this channel here, right? So there is no coordination. They're independent. The sensor measurement is independent of the state of the channel, right?
So D is a
Bernoulli
process.
Yes, this is a Bernoulli process, yeah. And but here, if you're talking about this, which motivated that little problem, right? There is no coordination between the agents.
Like Aloha.
Yeah, something like that. Yes, exactly. But Aloha is a randomized protocol, right?
Yeah.
Now, an interesting feature here is that randomization doesn't buy you anything in this case, in this problem, okay? But Aloha is trying to optimize something different. It's trying to maximize throughput.
The throughput of the whole network.
Yes, and here we are only interested in minimizing the mean square error between between the measurements and the estimate.
You want to transmit as much as you can.
Yes. So in communication networks, the packets don't have any meaning, right? We don't care about the contents of the packet, right? The packet is just something that you want to convey through the network. In here, we want to convey the measurements themselves. So the packets have, meaning. Does that make sense? Any other questions?
Okay, so let's thank our speaker for the